Hey guys, my name is Pedram and I'm a professional practice assistant professor in finance. I'm also a CFA charter holder. This is another episode of my crash course in machine learning concepts, simply explained. Alright, part 17, logistic regression. Logistic regression is a regression model that is mostly used for classification. So what does this mean? Well, remember, the output of the model are probabilities. For example, what are the probabilities of someone defaults versus not defaults? Imagine this is the data set that we are looking at, credit card default, right? On the vertical axis, we have default. On the horizontal axis, let's say we have account balance, remaining balance. As you can guess, if the amount of balance on a credit card is larger, the probability of that person defaulting is going to be higher, right? So the outputs of this logistic regression models are going to be some probabilities. For example, it says that for this guy, for this individual, the probability of default is, let's say, 80%. For this individual, the probability of default is, let's say, 30%. Then we have to come up with a threshold, right? So let's say we assume that if the threshold is 50%, we're going to call, if the probability of default is greater than 50%, that individual will default. If the probability of default is less than 50%, then that individual is going to not default, right? So if this is our threshold, then this individual is going to be classified as default, black. This individual is going to be classified as not default, right? White. So how do we come with this threshold? This is another issue that we're going to discuss about, right? And for example, if you want to be more conservative in terms of avoiding too many false positives or avoiding too many false negatives, we have to change this threshold. Now, before going over the details, let's see where we are and what's the plan for the day. So we are here, logistic regression. And as you can see, logistic regression is another supervised machine learning algorithm because both the inputs and outputs are given. And it is mostly used for classification, as you can see. We will be covering the logistic regression concepts in 3 parts. Part 17, which is this video, 18 and 19. In this video, I'll be talking about linear probability model and compare it with logistic regression, why we need to move beyond simple linear probability model, and what are the advantages of working logistic regression for classification. In part 18, I'll be talking about the maximum likelihood estimation technique, which we are going to use it to estimate the model parameters. And finally, in part 19, we're going to talk about classification performance metrics in general. Because this logistic regression is our first classification model, it is a good time to talk about the performance metrics for classifications in general. Namely, we will be talking about accuracy, precision, recall, F1 score, ROC, and area under the curve, AUC. All right, now let's dive into it. Let's start with the concepts of classification itself, right? In classification problems, we are dealing with qualitative variables, and the qualitative variables can be either nominal or ordinal. So nominals, for example, gender, race, ethnicity, colors, and etc. And ordinal, you can think of, for example, GPA, A, B, C, D, or GDP growth rate. We can think of a GDP growth rate in 3 classes, low, medium, high. So in these ordinal variables, the ranking matters and not the magnitude, right? The magnitude doesn't make any sense. So for example, I cannot say that if someone's score is A, it's worth twice as B, right? But I can rank them. A is better than B, right? So the qualitative variables are also referred to categoricals. And they are referred to categoricals because they fit the data into different categories. So in this example, for example, at the end of today, we are going to have 3 categories, blue, orange, and green. Classification is the process of predicting categorical variables, right? And we know that classification problems are quite common, perhaps even more than regression problems, especially in economics and finance. Now let's review some examples in finance. The first one, financial instrument tranches, right? So for example, what are tranches? Tranches are pieces of pooled collection of securities, usually debt instruments, that are split by risk or other characteristic in order to be marketable to different investors, right? Why does that matter, right? For example, you want to say that you look at the characteristic of a bond and see if that bond is an investment grade bond or a junk one, right? Because if you can figure out if it is investment grade or junk bond, or if bond goes from investment to junk, then it's going to, what happens to the price? The price is going to decrease. If the price of a bond decreases, its yield is going to increase. If the yield increases, the portfolio duration is going to change. And if the portfolio duration change, the portfolio manager should rebalance the entire thing. So as you can see, these simple decisions are going to become very, very important in finance, right? So this is just one example. Another one is that, for example, you're looking at online transaction and you want to figure out if that transaction was fraudulent or not. Another example, loan application. At the end of the day, you're working at a bank and you want to see if you should approve or deny someone's application based on some specified characteristics, right? Another one is credit card default. So this is the example that we started the lecture with, right? So you want to look at, someone's profile and their credit card balance and etc. And at the end of the day, make a prediction that if that guy is going to default or not, right? And finally, another example, we can think of car insurance customers. At the end of the day, if you're working at an insurance institution, you want to charge different people different premiums, right? And that premium should depend on if they're high risk, medium risk, or low risk. So this is another example of application of classification in, let's say, in finance. And as you can see here, most of the examples that I gave you, they are used for two-class classification, right? And we know that logistic regression by construction is widely used for two-class classification. So what if you have three classes, like here, 3 colors? What if you have 4 classes, 5 classes? So for these kind of questions, we can do multiple class logistic, or it's called multinomial logit, or also we can do softmax regression. So the idea of all these methods is breaking down the multiple class to multiple binary class. So for example, I have class here, this example, we have 3 classes, blue, orange, and green. So we have to say, okay, blue versus other, orange versus others, green versus other. So we break this problem into 3 sets, right? 3 different problems of classifications, right? So, but just I want you to remember that the logistic regression by construction is designed for 2-class classification. All right, now let's look at a real-world example to make sure that you're all on the same page and we understand what's the goal of classification in general, right? So here's an example from the Introduction to Statistical Learning textbook, the ICLR textbook, and we are dealing with 10,000 observations. And the data consists of monthly income and monthly credit card balance, right? And out of these 10,000 observations, there's only 300 of them which default. So the data is very, very imbalanced. However, here, for the representation purposes, we are going to look at the balanced version of the data, right? Let's say the blue ones are the no default, and the orange one are the default ones, right? So what's the goal? The goal is to come up with a classifier, to build a classifier that performs well both in train set and test set. Because remember, guys, the model is going to be trained in the train set, and at the end of the day, we are going to look at the performance of the model evaluated in the test set, not in the train set. So the goal is to come up with a classifier to make sure that that model is going to perform well both in train and test set. Now, let's think about it. Let's look at this data set, and this is in 2 dimensions, and the colors are, let's say this is our 3rd dimension, right? So we have balance versus income. And as you can see, Now we can think of different classifiers. So let me start by giving an example. Do you think that this is a good classifier? So if I call anything above this line, let's say default, and anything below this one, let's say no default, does that make any sense? Most probably not, right? Because as you can see, it seems that income is not a good variable to start with or to think about, right? So it seems that for different values of income, the default versus non-default is all over the place. So we have very high income earners that they no default, or at the same time they default, right? So, and the same story for very low income level people. Maybe the monthly income is very low, but even for those people, we have some observations that no default, or some observations that default. So it seems that all in all, this is not a good classifier, right? So how we should do that? We should think of a classifier that does a good job both in train set and test set. So let's look at another one. So maybe this one. Maybe this is a better classifier, right? So we can say, okay, anything on the right hand side is going to default. Anything on the left hand side of this classifier is going to no default, right? How do we come up with this line? So this is what we're going to do in this series of lecture, right? At the end of the day, the logistic regression is going to give us this decision boundary, this classifier. And with that, we're going to be able to classify the new observations, right? So let's see how it's done. We said that income is not necessarily a good variable to predicting if someone is going to default or not default, right? So if we need to pick only one feature, let's work with balance. Now, if I plot the balance versus default in the real world data, so how's it going to look like? So we will end up with many people that they have high balance on their credit card and they're going to default, right? And of course, there are some people with low balance, but they don't default. And on the other hand, many people with very low balance in their credit cards, and of course, they're not going to default. And the same story, maybe there are some people with high balance, but they still don't default. So let's say this is a representation of the data set, right? Just keep it very simple. Okay. And if you stare at this data set, you want to come up with a model, and that model should give you, for example, what is the probability that this guy is going to default? What is the probability that this guy is going to default, right? So if you stare at this very simple plot, you might say that, okay, let's go ahead and use a simple regression model. Why not, right? So if I use simple regression model, if I use OLS, it's going to give me something like this, right? And then I can say, okay, for example, this individual, the probability of default is 80%. Using simple regression, right? For this individual, the probability of default is 30%. So it seems that, simple regression is a perfect fit for this job, right? If you want to see mathematically why, so let's look at this. Let's stare at this regression line. We are regressing y, default or not default, on one variable, right? Just balance. Now, if I take the conditional expectations from both ends, what do I get? So on the left, I have the expected value of y given balance, given x, is equal to, because this y is a binary variable, we know that it's going to be equal to the conditional probability multiply the value of that binary. And y can take only 0 and 1. When y is equal to 0, this whole thing is going to cancel, right? It's going to be equal to 0. But when y is equal to 1, what do we have? The probability of y is equal to 1, default, multiply 1, and at the end of the day, we get this one. And this is, we show it with p of x, and that's basically the probability of success. In this case, default, when y is equal to 1, right? So this is our left-hand side, probability of default. And on the right-hand side, so if I take conditional expectation from the right-hand side, so what do I get? I get beta 0 plus beta 1 balance and plus expected value of epsilon given balance. So that's going to be 0, right? So it seems that, as I said, so mathematically also, it seems that simple regression is a perfect fit for doing this task, right? Because on the left-hand side, we have some probabilities. On the right-hand side, we have some simple equation for our regression, right? So that's why we call this simple model linear probability model, right? But what are the caveats of this model? So what do you think? Well, the first and most obvious disadvantage of this model is that the linear probability model is that it's going to make some predictions that are greater than 100% or predictions that are negative. How? Look at these observations. So for this observation, the model is going to predict a number like this, and it is, let's say, it's 120%, right? So this doesn't make any sense because the probabilities should be between 0 and 1. And look at this one. For this observation, it's going to make a prediction, let's say minus 20%. This also doesn't make any sense, right? So this is the first caveat, that the linear probability model is going to generate numbers greater than 1 or less than 0. It's not going to happen all the time, but it may generate those numbers, right? Another caveat is mostly from econometrics point of view. Remember, guys, this y variable is it comes from a Bernoulli distribution, right? Because it can take only 0, 1. So by construction, what is the variance of the Bernoulli distribution? So let's say variance of y is going to be by construction equal to p of x, probability of success, multiply 1 minus p of x, right? Probability of failure. So by construction, we can see that the variance of y is not constant, right? So it's a function of x. This means that this model is suffering from heteroscedasticity. Heteroscedasticity by construction, right? So we know in machine learning, maybe it's no big deal. We are not necessarily worried about heteroscedasticity because at the end of the day, the goal is to make predictions. But it is good to know that this model by construction is suffering from some heteroscedasticity problem. Okay. What are other disadvantages of linear probability model? Can you think of any others? And then why we should go beyond linear probability model? Well, what if the data is imbalanced? So let's look at this is a real representation of the entire data set. Let's say the 10,000 observations. In the previous example, I just showed you a balanced subset of the data. Now let's work with the 10,000 observations in the data set we know that it's highly imbalanced. At the beginning, I told you that only 300 of these guys are going to default, right? And now imagine, so as you can see, most of the observation is here, and only 300 observations is here, default, right? And if this is a real data set, and now if you use OLS, our linear probability model is going to be something like this. So this is a fitted line for linear probability model. And if that's the case, look at that. It's generating some probabilities below 0. So this is one problem. And another problem, look at that. Imagine at the end of the day, you want to use this linear probability model and in order to say that if someone is going to default or not, right? And if you pick this threshold, let's say the threshold is only 50%. Even for the threshold of 50%, the model is going to always predict no default. Does that make sense? Right? So if the threshold is 50%, as you can see, the model is whatever you plot here, the model is going to always predict some number less than 50%. So less than 50% is going to be assigned to no default. So the model always predict no default in this example. Right? So as you can see, these are the caveats of linear probability model. And for that reason, we have to move beyond that. So what's the solution? So the solution is, for example, if we use logistic regression. So logistic regression is going to take this linear probability model and transform it to an S-curve shape fit, right? And if that's the case, as you can see, all the probabilities are between 0 and 1 now. And on the other hand, we can have probabilities in this specific example, right? It's not always the case, but in this specific example, we can have probabilities that are 80%, 70%, and probabilities that are less than 50%. So here, even if you come with that 50% threshold, the model is not always predicting 0 or 1, right? So we're going to discuss about this threshold in more details in the lecture videos, in the future videos, but just remember that by default, the logistic regression is using 50% as a threshold. All right. All right, so let's see how we can transform this linear probability model into something like this. For that, we need to have a monotone mapping function that has a range between 0 and 1. So we need to make sure that this function has a range between 0 and 1 and it's monotone. So by monotone, in this case, we mean strictly increasing. If you take derivative at each point through the entire range of through the entire domain of the function, it's going to be in this example, let's say positive, right? So one of the better candidates out there is what we call sigmoid function. So sigmoid function is defined as this. Phi of z is equal to 1 divided by 1 plus e to the power of minus z, and it has all the characteristics that we need. Let's check it out. So first of all, if I send this z to plus infinity, then what will happen to phi of z? The phi of z is going to be equal to 1 divided by 1 plus e to the power of minus infinity. So this is going to converge to 1 divided by 1 plus 0, right? So it's 1. So as z go to plus infinity, the phi of z, the range is going to converges to 1. And if I send z to minus infinity, then phi of z is going to be equal to 1 divided by 1 plus 1 to the power of e to the power of minus infinity, which is plus infinity. So this is going to converge to 1 divided by 1 plus 1 plus infinity, which is 0. So this converges to 0. So it seems that yes, this sigmoid function is strictly increasing. If I take derivative, it's going to be always positive, right? And the range is between 0 and 1. Now we're going to use this mapping function and apply it to our linear regression model. At the end of the day, we will end up with what we call logistic regression. And now the blue line here is our linear probability model. So this is a linear probability model. We talked about the caveats. And the orange one is our logistic regression. Now let's see, why do we call it logistic regression model? Well, here's the model, right? And in machine learning language, let's write it in f of w and b of x, and it's equal to 1 divided by 1 plus e to the power of minus z. So this z is our right-hand side equation, which is wx plus b. So this is, if I have multiple features, we can get w1x1 plus w2x2 and etc. plus a bias term, right? In case of two classes, we know that this f of w and b is going to be equal to probability of success. So we proved it in the previous slides, right? Now, a bit of rearrangement will give us this log of odds, which is equal to the right-hand side. So let me quickly show you how we get there. So we said that, let me use blue. This is p of x. For short, let me write it p, and it's equal to 1 divided by 1 plus e to the power of minus, instead of wx plus b, I'm going to write it for short z, to just make our life a bit easier to do the proof, right? So I'm going to do this, so let's multiply p by the numerator. So we have p plus p to the power e to the power of minus z is equal to 1. Then we can single out for z, e to the power of minus z. So it's 1 minus p divided by p. So from this, if we just inverse it, we get e to the power of z is equal to p divided by 1 minus p, right? And now if we take natural log from both ends, what do we get? We end up with a log of p divided by 1 minus p is equal to z. So this is how we get from there to here. Now, if you look at it, this monotone transformation is called log odds. So that's why we call, or logit transformation. So that's why we call this equation logistic regression, right? And we know that logistic regression ensures that the estimates are always between 0 and 1. So now let's think about it. This is our logistic regression. Is it going to be a parametric model or non-parametric? It is parametric. Why? Because we are imposing some functional form to the model. So it's going to be a parametric model. And on the other hand, what else can we say about this model? Is this model interpretable or not? Well, the answer is yes. We can say if, for example, x increased by 1 unit, then the log of odds is going to increase or decrease by w units. So whatever w1 if you're looking at x1, right? So this is a parametric interpretable model. And now we have the model, and all we need to do is to somehow figure out what are the coefficients of the model. So we need to think of a solver that gives us W stars and the B star. Because if I have W star and B star, we are done. So we can throw new data at it and we can get some predictions. All right. Before concluding this video, let's talk about logistic regression fit or the decision boundary. Depending on how we define Wx plus B, we can get any of the following fits from logistic regression classifier. So let's start from this one. So imagine if I'm defining Wx plus B, and remember we're in 2D now, right? So if I define it like this, W1 x1 plus W2 x2 plus B, right? This is what we're going to get. We're going to have a linear classifier, right? The fit, the boundary is going to be linear. So anything on the right, we're going to call it, let's say, blue circle. Anything on the left, we're going to call it, let's say, the red cross. If we make this model more complex, right? So let's make it more complex. Why do we need to do that? So we are going to make it more complex. And by doing that, the bias is going to decrease, the variance is going to increase, right? So we are looking for a better fit, better balance between bias and variance, right? So if we make it more complex, maybe we end up with something like this: W1 x1 plus W2 x2 plus W3 x1 squared plus W4 x2 squared, and etc., right? Plus B. And now, and if you do that, we get this kind of boundary. So the boundary is going to be nonlinear. So even though the logistic regression model itself is a linear model, but the fit, the boundary, the decision boundary can be perfectly nonlinear, which we have the case here, right? And now let's make it even more complex. So let's make it even more complex. We know that if you make it super complex, it's going to overfit. This is complex. This is what we're seeing here, right? So this is obviously an over-complex classifier, right? And it's unnecessarily complex. What does it mean? It means that, so for example, we have W1 x1 plus, let's say, I don't know, W5 x1 to the power of 5, W6 x2 plus, I don't know, maybe W11 x2 to the power of 4, and we add the interactions and etc., right? So this model is unnecessarily complex, and as you can see, it's overfitting, right? Yes, maybe the bias is small. On average, we're hitting at the target, and it's doing a perfect job in the train set, right? This example is doing, we're going to talk about the performance metrics in the video number 19, I believe, part 19. But very simplistically, you can see there's no any sort of misclassification here, right? So maybe it's doing a perfect job. The accuracy of the model in the train set is 100%, but we know that it's going to overfit the train set, right? It means that if we look at the performance of the model in the test set, it's not going to do a good job, right? Finally, let's look at the logistic regression output for our credit card default example and see how does the decision boundary look like. So here's the model. This is our logistic regression model, the probability of y given x. So this is probability of default. This is what we call success here, right? Probability of y is equal to 1 given your feature space is equal to 1 divided by 1 plus e to the power of minus something, right? And this is using the sigmoid transformation. At the end of the day, if you want to visualize this, it's going to look like something like this. So we have income per month, balance per month, and then this is our logistic regression classifier. This is the boundary. Anything on the left, the green background, the model is going to call it 0, no default. Anything on the right, the red background, the model is going to call it 1, default. And the dots themselves are real observation. So for example, a green dot means no default, actually no default, and a red dot means actually default. So as you can guess, red dots on a red background is good news. Green dots on a green background is good news. These are the correct predictions of the models, and anything else are wrong predictions. So later on in part 19, we're going to talk about the performance metrics in classification. But until then, take care. See you in the next video.